Hello, everyone. We are here today for the Energy Transition During Energy Crisis team. So, a little bit of background right now is that Cape Town is facing an energy crisis because current power plants are breaking down just because of their just old age and there's not working as efficiently. So, one of the things that this leads into is load shedding. And the concept of load shedding is that basically it's intentional blackouts by governments and corporations, and that's obviously not great because then communities are held back from being able to do things since they just don't have their basic needs, and it affects low-income communities far more. So the idea here is to create an entire data pipeline starting with data processing, and that uses computer vision to detect solar objects. And based on that, we can create estimations on how much power is being used by these households, because the area of each of these solar objects is heavily proportional to the amount of power consumed. And this data is all important to implement proper policy grid planning in Cape Town.
Okay, for the dataset, so our dataset includes aerial imagery from Cape Town, and the data is georeferenced using a ESRI, and then ESRI system, and we use QGIS for annotations, perceiving spatial accuracy, and out of 2,802 high-resolution images, 268 had nearly 2,000 annotations across 4 categories, including solar panel, solar water heater, solar pool heater, and uncertain. And then we refined 15 of the most labeled images, producing over 5,000 high confidence annotation without uncertain labels. And for the data pipeline, we start with the large aerial images at 12,500 by 12,500 pixels, which are too big to process directly. So we first run YOLO model to detect for object detection on 1024 by 1024 tile to find solar objects using bounding boxes. And then we crop 320 by 320 batches around these detection and pass them to unit for semantic segmentation into solar panel, water heater, or pool heaters. And finally, we extract polygons from segmentation maps, calculate their areas, and map them using a coordination system to estimate solar capacity with spatial accuracy.
For object detection, we used YOLO, which is designed to identify oriented bounding boxes. As shown here, solar panels are installed in various orientations. It takes 1024 by 1024 images as input and crops the detected any solar object into 320 by 320 patches for semantic segmentation using UNet. To evaluate performance, we use mean average precision, which is a standardized metric in object detection tasks. For classifying detected objects by YOLO, we use UNet to identify their classes and generate pixel-wise segmentation masks. The performance of this segmentation task is measured using intersection over union.
Finally, we have post-processing, which uses a JSON file containing the pixels of the image with a solar panel, water heater, or pool heater. These pixels are grouped into polygons to create individual solar objects. We calculate the area of each solar object to estimate the power capacity, and finally convert the pixel locations of each polygon into longitude and latitude. Here we ran our entire data pipeline using the YOLO, UNet, and post-processing to obtain these results on an unseen test dataset. Our estimation may have a high relative error because of model limitations such as false negatives or edge cropping, and also data quality issues that may influence the ground truth. Some limitations of our work is that we only used 15 of the 2,800 images in order to design our pipeline, and we also may need to further check data quality due to our limited knowledge of certain solar objects. In the future, we want to improve the accuracy of our predictions by fine-tuning our model on more data and enhancing our post-processing. We also want to conduct a time series analysis to predict the year of installation for solar objects. That's the end of our presentation, and thank you for listening.